Now chapter number 2, electrostatic potential and capacitance. Now first we have to discuss the work done on moving charge in the given electric field. Okay, this particular part which we are going to discuss is not given to you in the text, but that is very important thing for this particular chapter. Now suppose as shown in the figure, you see a point charge capital Q, which one is placed at the origin of Cartesian coordinate system. Now in the surrounding of it, the electric field of this charge Q is prevailing. Now in that electric field, suppose we want to move charge small q from point A to point B. Point A have the position vector r1 with respect to the origin of Cartesian coordinate system, and point B have the position vector r2 with respect to the origin of Cartesian coordinate system. Now we want to move this charge small q from A to B. Now arbitrarily we consider two paths to move it from A to B. See here, suppose first we move it from A to C on the curved path, and then after we move it from C to B on the linear path, and we calculate the total work done. And then we will calculate the total work done on moving it from A to B on the path, A to D on the linear path, and then D to B on the curved path. So here we will calculate the work done on these two paths. Clear? When any charge Q is placed in electric field E, the force acts on it, that is Q into E. Clear? When we move this charge small q in electric field, means if we place it at different position, E is different one. It implies that the force is variable one. So here what we have to do? We have to displace charge small q by infinitesimal small displacement. And the displacement should be such a small so that the work done, that is for constant force, we can calculate it like that. And then after, by moving it with so many infinitesimal small displacements from one point to another point, for each displacement when we calculate the work done, and then after if we take the summation of all these, we will get the resultant or total work done. Clear? Now see, when any charge Q, that is placed in the electric field E, the force acts on it, that is Q into E. And now if it is displaced by infinitesimal small displacement dr, dr is such a small so that we can consider E as a constant for this particular displacement. Then this is the force, this is displacement, so we can say this is the work done on moving charge Q by infinitesimal small displacement dr in electric field E. Clear to all of you? Now, first we calculate the work done on moving charge Q from A to C. Okay, and then after from C to B. So here we can write the work done on the path A to C, that is Q integration A to C E dot dr. But see here, electric field of charge capital Q, that is radially outward. So at each and every point on this particular curved path, electric field is perpendicular to the path. It implies that at each and every point, E dot dr, that will be equal to 0 because E is perpendicular to dr. So we can say the work done to move charge Q from A to C in the given electric field, that is equal to 0. Clear to all of you? Now work done to move charge Q from C to B. So again we can write W for the path C to B, that is equal to Q integration C to B E dot dr. So we can write that is equal to Q integration. Now position C, that is at distance R1 from the origin, and position B, that is at distance R2 from the origin. So we can write the limits R1 to R2. Now electric field at a distance R, that is KQ upon R square, and in vector form we can write KQ upon R square into R caret dot dr, that is dr into R caret, because here the electric field and the displacement of our charge small q both are in the same direction. So unit vector for electric field and unit vector for displacement, that is considered same one, R caret, R caret. But we know R caret dot R caret, that is equal to 1. So we can write now KQQ into, now integration of 1 upon R square. So that is actually R raised to minus 2. So integration, that is R raised to minus 2 plus 1 upon minus 2 plus 1. So resultantly it will be minus 1 upon R, and the limits are R1 to R2. Now if we substitute the limits, first R equal to upper limit R2, and then after minus R equal to lower limit R1. But due to this negative sign, you can write KQQ into 1 upon R1 minus 1 upon R2. This is the work done to move charge small q from point C to point B. Clear to all of you? So the total work done on moving charge small q from A to B on the path A to C, then C to B. So that is work done on the path A to C plus work done on the path C to B. But A to C, that is 0, and C to B, that we derived here, it implies that the total work done on the path ACB, that is equal to KQQ into 1 upon R1 minus 1 upon R2. Clear? Now let's calculate the work done to move charge small q on the path A, D, B. Okay. Now see, on the path A, D, B, when we move charge small q from A to D, A to D, point A is at a distance R1 and point D is at a distance R2, and path A to D, that is straight line linear path. તો જો આગળ તમે જે કર્યું કે C to B આ પાથ ઉપર ચાર્જ Q ને મૂવ કર્યો ને જે વર્ક ડન કેલ્ક્યુલેટ કર્યું કે QQ into 1 upon R1 minus 1 upon R2. The same will be there for moving the charge small q from A to D. So work done A to D, that is KQQ into 1 upon R1 minus 1 upon R2. Now D to B. તો જો આગળ આપણે કેલ્ક્યુલેટ કર્યું A to C, that is the curved path. It is an arc with radius R1. Similarly, D to B, that is an arc with radius R2. So work done to move on path D to B, that will be equal to 0, exactly like we calculated for A to C. It implies that total work done on moving charge Q on the path ADB, that is equal to KQQ into 1 upon R1 minus 1 upon R2. Now here you can see this thing. If we move charge small q from A to B on the path ACB or ADB, the work done, that is same one. So W on the path ACB, that is equal to W on the path ADB. Clear to all of you? Now here the important thing, that is this one, we proved the electric field, that is the conservative field. It implies that work done to move charge Q in electric field from one position to another position, that does not depends on the path chosen to move, but it depends only on the initial and final position. તમે કયા રસ્તેથી એને એક પોઈન્ટ થી બીજા પોઈન્ટ ઉપર લઈ જાઓ છો, that is not important thing. The total work done, that depends only on the initial and final position only. Clear to all of you? So here we can say this thing, the work done on moving charge Q in the electric field over a closed path. Closed path લઈએ એટલે initial અને final position same આવે. તો જો initial અને final position બંને same આવે તો total work done 0 થાય. અથવા તો આને બીજી રીતે એવું પણ કહેવાય કે integration of electric field over the closed path, that is always equal to 0. This is important result. Now the topic, that is potential and potential difference. Now see, as discussed in the previous theory, we can write now the work done on moving charge small q in the given electric field from any point P to any point Q, that we can write WP to Q, that is equal to integration F external dot dr. F external, that is the force which we have to apply to do the work. Okay, now we can write that is equal to minus integration P to Q F electric dot dr. હવે અહીંયા આપણે આ નેગેટિવ સાઇન અને આ એક્સટર્નલ નું આ ઇલેક્ટ્રિક કેમ લખ્યું? તો આપણે ચાર્જને મૂવ કરવો હોય તો આપણે એની ઉપર ફોર્સ એક્ઝર્ટ કરવો પડે. એટલે આપણે એઝ પર ડેફિનેશન પહેલા એવું લખ્યું કે W ઇક્વલ ટુ ઇન્ટિગ્રેશન F એક્સટર્નલ ડોટ dr. પણ આપણે જે ફોર્સ એક્ઝર્ટ કરવો પડે છે that is against ઇલેક્ટ્રિક ફોર્સ. કારણ કે ઇલેક્ટ્રિક ફોર્સ જે છે એ ફોર્સ એટ્રેક્ટિવ પણ હોય, રિપલ્સિવ પણ હોય, બરોબર. અને આપણે જ્યારે ચાર્જને મૂવ કરીએ at that time we have to take care about this thing. There should not be the accelerated motion of the charge. એટલે આપણે એને ઇન્ફાઇનાઇટેસિમલ સ્મોલ ડિસ્પ્લેસમેન્ટ અને એટલું સ્લો કરાવવાનું હોય કે એને એક્સલરેટેડ મોશન ના આવે. તો હવે ઇલેક્ટ્રિક ફોર્સ જો એને રિપેલ કરતો હોય કે એટ્રેક્ટ કરતો હોય, બેમાંથી કંઈ પણ કરતો હોય, તો ચાર્જ તો એની અંડર ઇફેક્ટ એક્સલરેટેડ મોશન કરશે અને આપણે એની અગેન્સ્ટમાં વર્ક કરવું પડે છે. એટલે આપણે અહીંયા આગળ નેગેટિવ સાઇન મૂકી. સો વી કેન રાઇટ વર્ક ડન ટુ મૂવ ચાર્જ સ્મોલ q from P to Q in the given electric field, that we can write minus integration P to Q F electric dot dr. Now, this work done that will be stored in it in the form of potential energy. So we can write here the change in potential energy that is equal to work done. So UQ minus UP that is equal to W. Now this F electric that we can write Q into E. When any charge Q is placed in the electric field, the electric force acts on it, that is Q into E. So we can write UQ minus UP that is equal to minus Q integration P to Q E dot dr. Clear? Or here we can see, as per work energy theorem also, we can write the work done that is minus integration P to Q F electric dot dr, that is the change in potential energy. Clear to all of you? Now suppose we take the initial position P that is at infinity. That is at infinity. Infinity means outside the electric field. હવે જો ચાર્જ પોતે ઇલેક્ટ્રિક ફિલ્ડની આઉટસાઇડ હોય તો પછી પોટેન્શિયલ એનર્જી possessed by it that will be equal to 0. કારણ કે એ ઇલેક્ટ્રિક ફિલ્ડની અંદર ઇફેક્ટ જ નથી. So we can write UP that is equal to 0. તો પછી UQ that is equal to, you can write minus Q integration infinity to Q E dot dr. તો એનો મતલબ એ થયો કે the total work done in bringing charge small q from infinity to a given point in the electric field against the field, that is stored in it in the form of potential energy, and that is given by the equation U at position Q that is equal to minus Q integration infinity to Q E dot dr. Clear to all of you? Now, if we take this charge small q on left hand side, then we can say U at Q upon small q, that is nothing but the electric potential energy of unit positive charge at point Q, and the electric potential energy of unit positive charge at any point in the given electric field itself is called electric potential at that point, and that is denoted by capital V. So we can write electric potential V at position capital Q, that is equal to UQ upon small q, and that is equal to minus integration infinity to Q E dot dr. Clear to all of you? So that this one is VQ equal to minus integration infinity to QE dot dr, that we can represent like this: total work done against the field in bringing unit positive charge from infinity to the given point, that is called electrostatic potential at that point.
સર
So
ગ્રેવિટેશનલ
is
પોટેન્શિયલ જેવી જ છે.
so we can say this one is the definition of electrostatic potential at any point in the given electric field. Now, if we take the potential difference between 2 points in the given electric field, suppose we take VQ minus VP. VQ, that is the potential at point Q in the given electric field, and VP, that is the potential at point P in the given electric field. So VQ minus VP, that is the electrostatic potential difference between the points P and Q. So we can write now VQ minus VP, that is equal to UQ minus UP upon small q. Clear? So VQ minus VP, that we can write as per this equation. If we take this Q on left hand side, then that is minus integration P to Q E dot dr. So here, now we can say this thing: the potential difference between 2 points P and Q in the given electric field, that is the total work done against the field on moving unit positive charge from point P to point Q. Clear to all of you? In chapter number 1, we discussed about the electric field due to a point charge. Exactly like that, now we have to discuss electric potential or electrostatic potential, or simply we can say potential due to a point charge. Now, suppose we have a point charge capital Q, which one is at the origin of Cartesian coordinate system, and we want to find the potential at point P in its electric field, and point P have the position vector R with respect to the origin. So as per definition, what we have to do? As per definition, we have to bring unit positive charge from infinity to point P. Now, we have to calculate the total work done against the field in bringing unit positive charge from infinity to P, and that is called the potential at P. Clear? So we can write as per definition, potential at P, that is equal to minus integration infinity to P E dot dr. So we can rewrite this one as minus integration infinity to r, because point P, that is at a distance r from the origin. Now electric field at a distance r of a point charge capital Q, that we can give by the equation kq upon r square, and in vector form multiply it by r caret dot dr r caret. But r caret dot r caret, that is 1. So we can rewrite this one as minus kq integration infinity to r 1 upon r square dr. Clear to all of you? So integration of 1 upon r square, that is minus 1 upon r. So we can write V means potential at point P equal to minus kq into minus 1 upon r, and the limits are infinity to r. This minus minus plus, so we can write V at P, that is equal to kq into first r equal to upper limit r, so 1 upon r, then minus r equal to infinity, the lower limit, so 1 upon infinity. But 1 upon infinity, that is equal to 0. So we can write electric potential at point P in the electric field of point charge capital Q, that is kq upon r, or we can write that is q upon 4 pi epsilon 0 r. So here we can see this thing. The electric potential of a point charge, that proportional to 1 upon r. In previous chapter, we studied this thing. The electric field of point charge, that proportional to 1 upon r square. Clear to all of you? Example 2.1. A. Calculate the potential at point P due to charge of 4 into 10 raised to minus 7 coulomb located 9 centimeter away. B. Hence obtain the work done in bringing a charge of 2 into 10 raised to minus 9 coulomb from infinity to the point P. Does the answer depend on the path along which the charge is brought? Now see, the given data, that is charge Q, that is 4 into 10 raised to minus 7 coulomb. Distance r, that is 9 centimeter, so that is 9 into 10 raised to minus 2 meter. And we have to bring charge small q, which is equal to 2 into 10 raised to minus 9 coulomb from infinity to that given point. Okay. Now see, first the potential of a point charge. So that is kq upon r. K, that is 9 into 10 raised to 9. Q, that is 4 into 10 raised to minus 7 upon r, that is 9 into 10 raised to minus 2. So V, that is equal to 4 into 10 raised to 4. Its unit, that is joule per coulomb, and it is known as volt. Okay. Now, second question. See, potential at any point, that is nothing but the work done in bringing unit positive charge from infinity. Now here we want to bring charge Q from infinity to that point. So total work done, that is Q into V. Simple thing. Q, that is 2 into 10 raised to minus 9 into 4 into 10 raised to 4. And you will get the answer 8 into 10 raised to minus 5 joule. Then here it is asked, does the answer depend on the path along which the charge is brought? No. We already discussed this thing. The work done that does not depends on the path, it depends only on the initial and final position. Clear? Now, potential due to an electric dipole. Okay. Say, suppose as shown in the figure, the dipole that is on the y-axis plus q minus q, separation between these two charges plus q and minus q, that is 2a, and the dipole moment that is from minus q to plus q as shown in the figure. Now we want to find the potential of this dipole at point P, which one is at distance r from the center of the dipole, and the angle between the dipole moment and the position of the point, that is theta. Now at this point P, we want to calculate the potential. Clear? Now see, in previous theory we discussed the electric potential due to a point charge, and we derived the equation of it, that is V equal to kq upon r. Now suppose our charge q, that is negative charge, then simply we have to write the equation for the potential, that is minus kq upon r. It implies that we can say this thing: the electric potential of positive charge at any point, that will be the positive potential, and due to a negative charge, it will be negative potential. Here we have a dipole. Dipole have 2-point charges. So simple concept here. First we have to calculate the potential at point P due to positive charge, and then we have to calculate the potential at point P due to this negative charge, and then after we have to take the algebraic summation, because potential is a scalar quantity. Now say, suppose from charge plus q, point P that is at a distance r1, so we can write the potential of charge plus q, that is V plus, equal to kq upon r1. And if point P that is at a distance r2 from minus q charge, then its potential at P, that is V minus, equal to minus kq upon r2. So resultant potential at point P, that is V plus plus V minus. So we can write that is kq upon r1 minus kq upon r2. So we can write therefore V at P, that is equal to kq into 1 upon r1 minus 1 upon r2. But always we take the position of the point from the dipole, that is with respect to the center of the dipole. It implies that we have to represent the equation of the potential at point P in terms of R, not in terms of R1 and R2. Clear up to this one? Now see, suppose here we take the position plus Q to center A, that is vector A, and from center to point P as position vector R, then R1, that is the vector joining to the tail of first one to the head of second one. So we can say vector R1, that is equal to vector R plus vector A. Now what is the angle between R and A? So angle between R and A, that is pi minus theta. કારણ કે આપણે કોઈ પણ બે વેક્ટર વચ્ચેનો એંગલ લઈએ ત્યારે બંને વેક્ટરનું ટેલ આપણે સેમ પોઝિશનથી ઇમેજિન કરવું પડે. તો અહીંયા આ A નું હેડ આવ્યું, તો આપણે A ને ટેમ્પરરીલી આમ એક્સટેન્ડેડ ઇમેજિન કરીએ તો R અને A વચ્ચેનો એંગલ આ આવે. તો ઉપરનો એંગલ થીટા, તો આ નીચેનો એંગલ પાઈ માઇનસ થીટા. તો હવે ડિસ્ટન્સ R1 જો આપણે ફાઇન્ડ આઉટ કરવું હોય તો આપણે આગળ ઉપર 11th માં ડિસ્કસ કરી ગયા કે મેગ્નિટ્યુડ A પ્લસ B, that is under root A square plus B square plus 2AB cos theta. Exactly like that. R1, that is under root R1 R square plus A square plus 2AR cos angle between A and R, that is pi minus theta. બંને સાઈડ સ્ક્વેર લઈ લીધો આપણે, એટલે ડાયરેક્ટ ઇક્વેશન મેં લખ્યું અહીંયા R1 square equal to R square plus A square plus 2AR cos pi minus theta. Up to this one clear? Therefore, we can write R1 square equal to R square plus A square minus 2AR cos theta, because cos pi minus theta, that is minus cos theta. Now, on right hand side, if we take R square common, then we can write R1 square equal to R square into 1 plus A square upon R square minus 2A cos theta by R. Now, in the similar way, here we can write R2 square, that is equal to R square plus A square plus 2AR cos theta. And now again we take R square common on right hand side, then R2 square equal to R square into 1 plus A square upon R square plus 2A cos theta by R. Clear up to this one? Now here A, that is very much less than R. So we can neglect A square upon R square. Now if we neglect A square upon R square, then both these equations we can write like this: R1 square equal to R square into 1 minus 2A cos theta by R, and R2 square equal to R square into 1 plus 2A cos theta by R. Now, take square root on both the side. So R1 equal to R into 1 minus 2A cos theta by R raised to 1 by 2, and R2 equal to R into 1 plus 2A cos theta by R raised to 1 by 2. Now take reciprocal on both the side. So 1 upon R1, that is equal to 1 upon R into bracket 1 minus 2A cos theta by R raised to minus 1 by 2. કારણ કે આપણે નીચે લઈ જઈએ raised to 1 by 2, તો ઉપર ન્યુમેરેટરમાં લખીએ તો minus 1 by 2. Therefore 1 upon R2 equal to 1 upon R into 1 plus 2A cos theta by R raised to minus 1 by 2. Now use binomial theorem. So we can write 1 upon R1 equal to 1 upon R into 1. Now this power will be multiplied with this second term. So minus 1 by 2 into minus 2A cos theta by R. 2 cancelled, minus minus plus. So we can write 1 plus A cos theta by R. Similarly for this one, 1 upon R2 equal to 1 upon R into 1 minus A cos theta by R. Clear up to this one? Now substitute the values of 1 upon R1 and 1 upon R2 in this particular equation. Okay? So potential at P, that is equal to KQ into 1 upon R1 is replaced by 1 upon R into 1 plus A cos theta by R minus 1 upon R2 is replaced by 1 upon R into 1 minus A cos theta by R. Take 1 upon R common. So KQ by R into, simplify this bracketed term. So 1 plus A cos theta by R minus 1, and this minus minus plus A cos theta by R. 1 cancelled. So we can write this is equal to KQ, or we can write K, that is 1 upon 4 pi epsilon 0. So Q upon 4 pi epsilon 0 R into this plus this, that is 2A cos theta by R. Therefore, potential, that is Q into 2A cos theta upon 4 pi epsilon 0 R square. Clear to all of you? Now, Q into 2A, that is the dipole moment P. So we can write V, the potential at point P, that is equal to P cos theta upon 4 pi epsilon 0 R square. Or you can write that is equal to P dot R caret upon 4 pi epsilon 0 R square. Here you can see this thing, the potential of electric dipole that proportional to 1 upon R square. And it depends on theta also. It implies that it depends on the angle between dipole moment and the position of the point. Clear to all of you? Now, the special cases. Electric potential on the axis of the dipole. Suppose we consider the point on the axis towards positive charge, then theta will be equal to 0, because the dipole moment and the position vector both will be in the same direction. So if in equation of potential we take theta equal to 0, then we can write potential, that is P cos 0 upon 4 pi epsilon 0 R square, but cos 0, that is 1. So potential, that is P upon 4 pi epsilon 0 R square. But if we take the point on the axis of the dipole towards negative charge, then the dipole moment that is from negative to positive and the position vector that is towards negative, it implies that the angle theta, that is pi. So potential at the point, that is P cos pi upon 4 pi epsilon 0 R square. Cos pi, that is minus 1. So potential at that point, that is minus P upon 4 pi epsilon 0 R square. Clear? Now potential at any point on the equator. So at any point on the equator or equatorial plane, theta, that is 90 degree, angle between the dipole moment and the position vector, that is 90 degree, and cos 90, that is 0. It implies that potential at any point on the equator of the dipole, that is always 0. Clear to all of you?